An 800-year-old roof beam may exhibit greater structural integrity today than at its time of installation, while contemporarily sourced lumber often experiences significant deformation within weeks. This discrepancy suggests that medieval builders possessed an understanding of timber characteristics and handling that has largely been superseded, a realization that may provoke considerable consternation. Medieval timber harvesters employed a sophisticated diagnostic process rather than mere felling. Prior to any incision, trees were meticulously evaluated, akin to a medical examination. Observations included bark morphology, branch angularity, and crown structure. A deviation from rectilinear growth indicated the presence of twisted grain, a critical defect for structural applications, particularly in roof beams, due to its propensity for failure. Furthermore, an auditory assessment was performed by tapping the trunk. A resonant sound signified dense, sound wood, whereas a dull thud indicated internal anomalies, such as rot or hollow cores, undetectable externally but discernible through trained auditory perception.
Geographic influence significantly influenced timber quality. Trees cultivated on north-facing slopes were highly prized due to inhibited growth rates resulting from reduced solar exposure. This slower maturation fostered greater ring density, approximately 40 rings per inch compared to 8 in rapidly growing southern slope counterparts, directly correlating to enhanced structural strength. Trees impacted by lightning or fire were rigorously avoided, as historical practitioners recognized that such trauma introduced internal stress fractures, potentially compromising structural integrity decades after initial installation. Expert timber selectors demonstrated remarkable foresight, accurately estimating a beam's service life within decades, a testament to which a structure's enduring for 800 years. In contemporary practice, lumber acquisition is primarily governed by dimensional specifications and cost, with little regard for species-specific properties or individual tree characteristics. However, timber selection represented only a singular facet of traditional expertise. The precise timing of felling proved equally pivotal.
The practice of felling trees according to lunar phases, often dismissed as folklore, has received empirical validation. German forestry research has demonstrated that timber harvested during the waning moon period, between full and new moon, exhibits a 4 to 5% reduction in moisture content compared to other lunar phases. While seemingly marginal, this initial moisture differential significantly expedites the prolonged drying process essential for timber. This phenomenon is attributed to the moon's gravitational influence on plant sap flow, analogous to tidal forces, which draws sap downwards towards the roots during specific lunar periods, thus yielding naturally drier raw material. Medieval guild statutes mandated precise felling dates, with non-compliance incurring severe professional penalties, including expulsion. This methodology was further augmented by winter felling, leveraging the dormant state of trees when most moisture had been sequestered in root systems. Consequently, winter felling during a waning moon phase ensured the acquisition of timber with minimal inherent moisture. In stark contrast, contemporary commercial logging operates continuously, prioritizing operational efficiency and mill throughput. This relentless harvesting often results in lumber delivered to construction sites predisposed to issues such as warping, checking, and premature decay, frequently prior to installation. This shift represents a departure from naturally informed harvesting schedules in favor of expedited processing. However, lunar timing constituted only one aspect of traditional timber management. The subsequent treatment of freshly felled or green wood revealed further sophisticated practices. Contrary to modern perceptions that deem freshly felled, high-moisture green wood unsuitable, medieval carpenters intentionally utilized such material. This approach was strategic. Green timber exhibited superior workability, allowing for precise joint shaping with hand tools with significantly reduced effort compared to kiln-dried equivalents. The fundamental principle, however, manifested post-assembly. Recognizing that wood shrinks anisotropically, approximately twice as much tangentially across growth rings as longitudinally along the grain, builders deliberately constructed mortise and tenon joints with slight initial oversizing. Upon the insertion of a dry oak peg, the subsequent natural drying and shrinkage of the green timber over decades induced progressive compression, leading to a permanent, self-tightening mechanical bond. This technique, requiring precise calculations to account for predictable shrinkage, resulted in joints of extraordinary and increasing strength over centuries, a testament to which are 14th century joints inseparable, even with mechanical leverage.
Contemporary construction largely mandates kiln-dried lumber due to its perceived predictability, uniformity, and rapid availability. However, kiln drying involves high-temperature thermal treatment that prevents cellular relaxation, leading to internal stress accumulation and the formation of checks, cracks that compromise structural integrity and facilitate ingress for water and insects. Medieval greenwood construction, by contrast, largely circumvented these issues. A key differentiator in their methodology was an unprecedented commitment to prolonged air drying. Proper air drying of oak, for instance, requires approximately 1 year per inch of thickness. A 12-inch beam thus necessitated over a decade of curing. Historical records confirm this practice, with timber for monumental projects like Notre Dame's roof being felled 50 to 80 years before installation, often requiring multi-generational planning. This extended, gradual drying allowed for cellular relaxation and gradual adjustment, preventing internal tension and stress fractures, which stand in stark contrast to the rapid heat-intensive processes of modern kilns that can damage cellular structure, akin to the difference between slow roasting and rapid microwaving of food products.
Furthermore, the stacking methodology during air drying was crucial. Timber was carefully arranged on raised platforms with precise spacing between individual boards to ensure optimal and uniform airflow from prevailing winds. This deliberate, engineered airflow contributed significantly to the material's final properties. Comparative testing reveals that air-dried oak can be 20–30% stronger than kiln-dried oak of identical species and grade, a performance differential attributable to the preservation of cellular wall integrity. This illustrates a historical preference for patience over expediency, resulting in enhanced structural durability. Beyond drying protocols, medieval builders possessed a profound understanding of wood species selection, a knowledge base often overlooked in contemporary construction, which significantly influenced the longevity of structures. Oak was preferentially employed for load-bearing elements, such as posts and beams, where significant compressive strength was required. Its natural tannic acid content provided inherent resistance to insect infestation and fungal decay, thus addressing dual preservation challenges. Elm, characterized by its tightly interlocked grain, demonstrated exceptional resistance to splitting and was therefore specified for submerged applications, including water wheels, ship keels, and well linings, where prolonged exposure to water was anticipated. chestnut was utilized in roof framing, notably for its tannin-based insect repellent properties, which prevented the accumulation of cobwebs in vaulted ceilings, thereby addressing maintenance concerns through material science. Ash, with its long, shock-absorbing fibers that resist splintering, was the material of choice for tool handles and weapon shafts across Europe, a property that minimized impact shock. For longbows, ash was selected not for its flexibility, but for the distinct mechanical behaviors of its hardwood, confessing on the bow's belly, and sapwood stretching on the back, allowing a single piece of wood to perform opposing functions simultaneously, a critical factor in the efficacy of English archery.
Modern construction, conversely, often relies on fast-growing, commercially cultivated pine, resulting in a soft, structurally weaker, and uniform timber applied indiscriminately across diverse applications such as decking, framing, furniture, and fencing, irrespective of specific structural or environmental requirements. This approach, while economically driven, neglects material optimization. Furthermore, medieval preservation techniques evinced an empirical understanding of material chemistry centuries before its formal recognition. Some of these methods, initially appearing unorthodox, proved remarkably effective. Consider water-based preservation. Medieval artisans submerged timbers in continuously flowing streams for extended periods. This constant flow effectively leached out soluble sugars and starches, the primary food source for fungi and insects, leaving behind a predominantly indigestible cellulose matrix. Another method involved bog oak, where timbers preserved in anaerobic, tannic-rich peat bogs for millennia remained workable, their integrity maintained by the absence of oxygen and the pickling effect of tannic acids. Medieval shipwrights also employed surface charring, deliberately burning timber surfaces to create a carbonized layer that acted as a physical barrier, resistant to insect attack and water penetration. Recognizing that end grain absorbs moisture at a significantly higher rate, approximately 200 times, than side grain, exposed beam ends were meticulously treated with linseed oil to impede moisture absorption. A more unconventional yet effective method involved burying timbers in manure heaps. The ammonia generated from decomposition permeated the wood, functioning as a potent fungicide. While modern pressure-treated lumber utilizes compounds like chromated copper arsenate, effective but environmentally hazardous due to chemical leaching and toxic waste generation, medieval approaches leveraged natural, albeit sometimes malodorous, organic substances such as fish oil and animal dung. Effective timber preservation was intrinsically linked to symbiotic architectural design. Medieval structures were not merely robustly constructed, but specifically engineered to facilitate the natural respiration of wood. Builders intentionally incorporated air gaps behind wall timbers, understanding that trapped moisture is a far more destructive agent than direct precipitation. Timbers allowed to wet and subsequently dry could endure, whereas prolonged dampness invariably led to decay. Furthermore, the substantial roof overhangs, often extending 3 feet or more, served a critical functional purpose beyond aesthetics, to prevent rain splash from reaching foundation timbers, thereby mitigating moisture ingress from ground rebound. The strategic use of stone plinths, elevating ground floor beams by as little as 4 inches above damp earth, effectively isolated timber from ground moisture. Additionally, the deliberate placement of windows and doors generated cross-ventilation, ensuring continuous airflow around structural timbers, which prevented condensation buildup and consequently inhibited rot. In contrast, modern construction frequently employs plastic vapor barriers within wall assemblies, ostensibly for protection. However, this practice often inadvertently creates stagnant, humid environments that accelerate timber degradation. A 2019 study revealed that 68% of structural wood damage in failing modern homes occurred in walls where plastic sheeting trapped moisture. This suggests a systemic engineering of vulnerability, whereas medieval builders meticulously integrated drainage and airflow. Beyond facilitating timber respiration, their strategy extended to fastener selection. The pervasive use of iron nails in modern construction presents inherent issues. Rust formation induces expansion, leading to wood splitting and creating conduits for moisture ingress into the timber's core. Medieval builders largely eschewed metal fasteners, opting instead for wooden pegs or tree nails. These pegs were crafted from wood with a lower moisture content than the timbers they joined, ensuring that as ambient humidity increased, the pegs absorbed moisture, swelled, and thereby tightened the joint over time, enhancing structural rigidity, a mechanism antithetical to the weakening effect of rusting metal fasteners. Furthermore, scarf joints were employed to connect timbers end to end, using intricately interlocking wedge shapes. A notable advantage of this design was its capacity to self-tighten under compressive load, meaning the structural integrity of the connection proportionally increased with the weight it bore. Dovetail joints, known for their self-locking design, demonstrate remarkable longevity. Examples in 400-year-old furniture consistently maintain structural integrity. In contrast, contemporary construction relying on mechanical fasteners often exhibits compromised stability within a significantly shorter time frame. The superior resilience of medieval timber framing is particularly evident under seismic stress. Lacking adhesives, these structures endured centuries of seismic activity due to the inherent flexibility of their joinery. This design allowed for dynamic energy absorption, permitting the structure to deform and then return to its original configuration, thereby dissipating seismic forces. Conversely, modern rigid connections are prone to brittle failure under similar conditions. A significant concern in modern construction is the extensive reliance on metal fasteners. An average American residence may incorporate approximately 20,000 nails, each representing a potential point of corrosion, a pathway for moisture ingress, and a long-term vulnerability for structural integrity. Beyond fastener selection, medieval builders possessed a nuanced understanding of wood as a material, particularly the distinction between heartwood and sapwood, a critical differentiation often overlooked in contemporary practice. A fundamental disparity exists in modern lumber yards, where wood is often treated as a homogeneous material, contrary to historically sophisticated practices. A single tree trunk comprises two distinct wood types: heartwood, the dense, darker central core, and sapwood, the lighter outer growth rings. These exhibit vastly different performance characteristics, a distinction medieval craftsmen rigorously applied. Heartwood is characterized by its accumulated natural defenses, including tannins, oils, and resins, which confer inherent resistance to insect infestation and fungal decay. Sapwood, conversely, lacks these protective compounds, rendering it susceptible to biological degradation. Consequently, medieval builders meticulously removed all sapwood from timbers designated for structural applications. This practice, despite resulting in the discard of 30 to 40% of a log's volume, was a deliberate choice founded on material performance. For instance, oak heartwood exhibits up to 5 times greater decay resistance than sapwood from the same tree.
Even within the same species, forest and felling period, this performance differential persists. Furthermore, sapwood possesses hygroscopic properties, absorbing moisture rapidly and exhibiting greater dimensional instability. Its nutritional composition also makes it particularly attractive to wood-boring insects, effectively accelerating its degradation. Empirical observations frequently confirm these differences. For example, a structural timber may show localized advanced decay in its sapwood regions, while the adjacent heartwood remains sound. Modern sawmill operations, driven by maximization of board footage, typically disregard these distinctions, processing logs indiscriminately and integrating both heartwood and sapwood into finished lumber. Beyond material selection, medieval construction emphasized rigorous standards for craftsmanship and accountability. This holistic approach forms a significant contrast with contemporary building practices. Medieval artisans provided personal guarantees for their structural work, often extending for a minimum of 40 years. Failure of a structural component carried severe professional and economic repercussions, encompassing loss of reputation, guild membership, and livelihood. This stringent accountability fostered an uncompromising commitment to quality in construction. Guild systems institutionalized these standards across generations, ensuring uniformity in techniques, joinery, and material selection among masters, regardless of geographic location. This pedagogical model facilitated the precise transfer of expertise from master to apprentice, establishing quality not as a commercial attribute, but as a fundamental imperative for professional continuity. A striking example of this long-term perspective is found in the practices of cathedral carpenters, who would engrave assembly marks into timbers. These marks, remaining legible and functional after 600 years, illustrate a profound sense of responsibility for future generations and maintenance, rather than mere self-aggrandizement. Furthermore, medieval builders routinely incorporated a substantial safety margin, oversizing structural components by 30 to 50% beyond calculated requirements. This proactive approach accounted for unforeseen future stresses, such as seismic events, conflicts, or increased load demands from subsequent modifications. In stark contrast, modern building codes often stipulate minimum structural lifespans of 30 to 50 years, effectively designing structures for planned obsolescence. This contributes to a pattern where the average contemporary residence may require significant structural remediation within 25 years, whereas medieval timber frames frequently endure for centuries, often surpassing the longevity of the civilizations that constructed them. The Greenstead Church, for instance, constructed circa 1060, stands as a testament to this durability, predating the modern English language. The decline in durable construction practices reflects not merely a loss of technical proficiency in timber construction, but fundamentally a departure from the underlying philosophy that prioritized enduring structural integrity.